section 13.1, sections like 13.1 and 13.2, and we're going over space curves. So now we discussed the vector function. Vector function, let's say R of t, and the components are f, g, and h. Then the curve C in R3 with parametric equation x equal to f of t, y equal to g of t, and z equal to h of t is called the space curve parameterized by R. And so basically what we see as the image of R is going to be a space curve. And so the next is example 3. Let's describe the space curves. So let's see if R of t is equal to t, 1 plus t, and 1 minus t. C is a line. In fact, what I can do is I can basically solve x is equal to t, y equal to 1 plus t, z equal to 1 minus t. And we're familiar with this one, that is a line. Now, what about R of t equal to cosine of t, sine of t, and t? Well, we just did one. That was cosine of t, sine of t, and 1. And that was a circle. In fact, if I didn't have a component here, and I was just looking at the trace on x and y plane, it would be a circle. And so it's a circle if I look at the trace on the xy plane, but then it also the third component is just increasing and going up as t gets bigger and bigger. So using this, I can see that the space curve looks like this one. And so here I can look and see from above, I can see a circle, and then basically as t increases, we go round and round the circle and up. So it's a spiral, and it's called helix. Now, r prime of t equal to t cosine of t and t sine of t for t bigger than equal to 0. This is a conical spiral, and that looks like that one. And so you can tell that as t increases, it's a spiral. We've seen this in parametrization in Calc 2. And now I'm noticing what I did is and you're noticing what I did is I omitted the t for y. So as t approached this, t gets bigger and bigger, the trace on the two other variables, which is x and y, is going to look like a spiral. And then that t is just bring it into the 3-dimension sort of. And for both of these, we assume t is bigger than equal to 0 for part 2 and part 3, but it's also possible to draw these in when t is it's the entire real numbers. In that case, the spirals continue to the other direction as well. And this is the conical spiral. Again, you look at the trace or at the projection on the xz plane, and you see that looks like just a spiral, and then you pull it out like that. And on the y direction, it expands that direction. Something to notice is that be aware of is that a single space curve can be parametrized by infinitely many different vector functions. We've already seen this with lines, right? You've seen multiple ways of parametrizing a line. Now, here, for example, all these values that you see in here give you the same helix. This is the helix that we discussed right above, and then we have this helix. And so if I get u equal to 3t and replace it in there, I'm going to get the same helix. And so I will get the same image, basically. And again over here. And then for basically they give you the same points, but for different t's, basically. And so the images are the same. And in here, can you get the same helix as the other two? It's just that if you assume t is bigger than 0 over here, you will have to assume t is less than 0 over here, for example. And so now, when we're studying the space curves, we often want to make sure we can tell the difference between properties that are extrinsic, those are the ones that are depending on the parameterization, and those that are intrinsic, which depend only on the curve itself. So what is depending on the curve itself? An example of that, so intrinsic could be how curvy the curve is, or the arc length from a point to another point, or things like that. And then extrinsic could be how fast something is traveling on the curve, and that sort of things. iClicker question 13.1b. Which one of the following does not parametrize a line? And so I suggest to pause and come back. Okay, so hopefully you paused. Now let's look at these. Some of them I can't tell. So the first one, x equal to 8 minus t, y equal to 2t plus 6, z equal to 3t minus 3. This is exactly the equation of a line. Now, go over here. Is this an equation of a line? So here, x is 3, y is t to the power cubed again, and z is t cubed. So basically, x is equal to y equal to z. Also, I know this is an equation of a line. Over here, x is equal to 8 minus t, y equal to 2, and z equal to 3. And z equal to 3. Y equal to 2, z equal to 3. So in this case also, I know that and it's just a line perpendicular to YZ axis, YZ plane, and going through point 2 and 3. So it goes to point 2 and 3, and it's perpendicular here, YZ 2 and 3, and it's perpendicular and coming out this direction, basically. And so that's a line also. What is remaining is here. If I solve for y, I can see, if I solve for t, I see x is equal to 8 minus 4t cubed, and t cubed is 8 minus x divided by 4. And then I've solved for t over here. Y is equal to 2 plus 5t squared, and t squared is equal to y minus 2 divided by 5. And then take the root and set them equal to each other. You realize it's not a linear relationship between these two. So this is the answer.